Okay, recording has started, so good morning, everybody. Welcome back to Math 115. Looks like Robert has made his way back into the class. Did you ever figure out what was going on with Teams, Robert? I'm hoping it wasn't an issue on my end somehow. Gotcha. Yep, that's about the extent of my tech advice that I can give anyone, so. Well, in any case, glad to have you back. All right, so today, hopefully, I'm going to get you guys a bit more involved. So, like I said, what we're kind of moving towards now is going to be a bit more maybe subtle takes on trigonometry. Okay, and we're going to do our best to answer different questions about trigonometric equations under differing circumstances. And in service of this, we're going to call upon our knowledge of all of the formulas, identities, and various interpretations of trigonometry, including, we might call upon the periodicity of the function, or the even and oddness of the function, or we might look at the graph of the unit circle and try to understand what these things mean geometrically. And we're going to use this whole kind of library of things which we have kind of built up about trigonometry to try to now answer some more interesting questions, maybe. Okay, so last time I kind of got us started off with a basic type of question that we could ask. And that question was, okay, well, when or for which x values are we going to have that sine of x is equal to cosine of x? Okay, and we had like 3 different ways of thinking about that. We could think about it literally in terms of the equation. Okay. We could think about it in terms of the equation. We could think about it in terms of the graphs of these two functions. Well, we know that these equations will be equal whenever their graphs cross. Okay, so we can try to find the places where the graphs cross. Okay, or we can try to find, well, take a look at the unit circle and kind of interpret, well, what does it mean for sine and cosine to be equal? It means that the x and y values of the point on the unit circle are equal to one another. And we can think about the 2 places on the unit circle where that happens, and we can consider the values of all the angles which point in those 2 directions. Okay, so this was how we finished up, and maybe I'll return to this in a minute. Say a little bit more about it. But first, let's remind ourselves that there's going to be an exam on Thursday, April 8th. So that's 2 days from now. And that's from 8 a.m. to 9 o'clock p.m. All right, I've said a lot about the exam so far, including ways in which I would recommend that you study. So if you want to see those, go back and watch the YouTube video from Monday of this week, which is week 13. on YouTube, and you can check that video out. So this is just a reminder for anybody who might be tuning in now that hasn't been tuning in recently. Okay, so one final way that I wanted to think about this this thing would maybe be, why don't I put it all the way up? Maybe be based on their equations. So I already showed us, well, how can we interpret this based on the graphs, and how can we interpret this based on the unit circle? I'll show you one final interpretation, and then we'll move on to something which is a little bit more collaborative. So this final interpretation is to consider, well, what is the difference between the sine and cosine graph in terms of transformations? And we've talked about this several times. We said that, well, the sine function just looks like the cosine function that's been moved over a little bit. Okay, in particular, it looks like the cosine function has been moved to the right by pi over 2 units. So if I want to interpret when is it going to be true for sine of x to be equal to cosine of x, well, I can rewrite that sine of x is equal to cosine of x, but that graph got shifted pi over 2 units to the right. Okay, pi over 2 units to the right. I'm sorry, not to the right, to the left, right? Let me go back and look at the graphs. Okay, so we shift sine to the left. So if we want to make a shift which goes to the left, I should add pi over 2 on the inside. So plus pi over 2. And we have that this is equal to cosine of x. Okay, so we have cosine of x plus pi over 2 is equal to cosine of x. Okay, and I know that cosine is 2 pi periodic, which means that x could be if these two things are equal. Okay, if cosine x plus pi over 2 and x cosine of x are equal, then I know that x plus pi over 2 and x should be 2 pi units apart. So we can solve the following in the following equation. If we want to express the distance between x plus pi over 2 and x, well, the distance between 2 points is the absolute value of their difference. So we'll do x plus pi over 2. Minus x. I really thought this was going to work out, but now it seems like it's not going to work out. Aha, that's why. Equals, no, what do I want this? What do I want to happen? What do I want to be true? I want x plus pi over 2 to be equal to x plus 2 pi n, where n is an integer. That's coming from the periodicity of cosine. Okay, then these two functions evaluated at x plus pi over 2 and x will be equal as long as x plus pi over 2 is equal to x plus 2 pi times some integer n. Okay? This is coming strictly from the periodicity of the cosine function. So if this is true, then what can we say? Man, hang on. Maybe I've got myself really into a corner here. Yeah, this is not going to work, is it? What is going on here? Okay, let me think about this for a second. We've got cosine of x, which is this repeating function. We know that it repeats on an interval of 2 pi, from 0 to 2 pi. So if we have sine of x is just cosine moved over by pi over 2, and we want to find out the x values for which this is true. We need to find the x values such that on a distance of basically pi over 2 apart, the height is going to be the same on these two functions, where this distance here is pi over 2. So we should not really be looking for some solution based on the periodicity of cosine. It's going to happen not because of the periodicity, it's going to happen because these function values repeat themselves on an ordered basis like this, which means we're going to actually have to look at the unit circle. And we're going to have to decide, well, if we have a difference in angles of pi over 2, so if we essentially have a difference, if we have a difference in angles of pi over 2, and then we take this thing and we like rotate it around in the unit circle, of course, okay. No. Man, this example is really not working like how I wanted it to work. Okay, but if we had this thing in the middle here, and we essentially rotated it around, we want to look for places where we can put a difference in our angles of pi over 2 and get the same value of cosine, which means that the x value of our points should be the same. If the x value of our points on the unit circle is going to be the same, that means we're going to be facing in this direction, such that we get the point, such that we get these 2 points here, which are the points x comma y and x comma negative y. Or it's going to be facing in the direction over here, in which case we get the points here, which are going to be negative x comma y and negative x comma negative y. And if we measure the angles, which are going to produce this, we're going to get, well, any angle which is originally coterminal to this angle, which is 7 pi over 4, and any angle which is coterminal to our original angle here, which is, what, 3 pi over 4? Okay, so it turns out that this method of looking at this thing, okay, did not work out that well. Sorry about that. I thought it was going to work, but it totally didn't. So that just goes to show you, you're always learning things in math, even at my level. Okay, well, sorry guys, that was kind of a waste of time. Hopefully, I guess the takeaway from this was that maybe we shouldn't have expected the periodicity to come in to this equation, since x plus pi over 2 and x are, of course, not going to be 2 pi units apart. They're going to be pi over 2 units apart because, well, if you look at the difference between, like what I was trying to do, if you take x plus pi over 2 and you subtract x from it, well, what are you going to get? You're going to get two angles which are pi over 2 units of measurement apart from one another, which is why I drew this kind of like right angle in here, and then I just spun it around until I found that the value of cosine would be equal for the 2 points which are given on the unit circle. Okay. Well, not everything in life works out. All right, let's move on to a new question. Okay, a new question. And I want to work with you guys collaboratively on this one. Okay, let's start this question by taking maybe 2 minutes to start thinking about it on our own. Okay, and then we'll work together as a group to try to solve it. So I'll ask for some initial steps. So don't prepare a rigorous answer per se, but start thinking about how we're going to approach this problem and maybe have some ideas of how to move through it. So take a couple minutes to try this one on our own. What we want to do is find the value of x, which is between 0 and 2 pi, such that the function 2 times sine of x minus pi over 4 is equal to 2. Okay, this is what we want to solve. Okay, so take 2 minutes to try on your own, and then we'll go through the steps to solve it together. Okay. So let's come back as a group. And we'll try to go through this together. So first, let me ask in general, if you guys tried either a graphical or an algebraic or a unit circle approach. I'm just curious to see which one was the most popular among the students that tried this problem. So what do we think? Did anybody find success with one of these three methods? Graphical, of course, would have to do with the graph of sine of x somehow. Algebraic would have to do with some manipulation of this equation. Then a unit circle would, have to do with some kind of properties of, well, sine is the y value of a point on the unit circle. Okay, Heidi says she used a graphical approach. Difference formula. That's an interesting take. Very interesting take, actually. I'm curious to see how that worked out. We'll do that one later. We'll check that one out. Sam wants to run through all three. Of course, we're going to do that, for sure. Okay, well, maybe I can ask, can anybody give me a good first step for the graphical approach of solving this equation? How do I interpret this equation graphically? Catherine, there's no dumb questions. The question is, what is this kind of problem called again? Well, this, I guess, would fall into a class of problems which I would call trigonometric equations. Okay, it's just an equation involving a trigonometric function. There are a bunch of other kind of topics which are implicit. For example, if you're going to take the graphical approach, then the approach is to consider this function as a transformation of sine of x. Okay, in which case you're also talking about transformations. Okay, but if you take the algebraic approach or the unit circle approach, then you're going to be talking about something else. Does that answer your question? Okay, cool. All right, so let's take the graphical approach. And let's try to understand, why don't we just start by trying to understand the graph of the left-hand side. Okay, 2 times sine of x minus pi over 4 comes from 2 sine of x minus pi over 4 is the graph of sine of x under what transformations? We've got 2 transformations. Can someone tell me what they are? For 2 sine of x minus pi over 4. That's right, we've got a phase shift. Phase shift to the left or to the right? Yeah, shift to the right. Okay, phase is also means horizontal. Okay, and what's the other transformation we have going on here? Yeah, amplitude or vertical stretch multiplied by 2. Okay, so how should I draw this? Let's start with just the sine function. Okay, I know the sine function starts at 0, 0, and then it goes up like this, and then comes down, and then comes back, right? So here's sine of x. Someone tell me, what is this distance from here to here on the sine function? The amplitude of this original sine function should be what? Well, of the original sine function, it's 1, right? We're getting to the 2 part. So if we apply then a vertical stretch by a factor of 2, then our 2 sine of x looks something like this. Where we go basically up to 2 now instead of just down to -1. Okay, so this looks like sine of 2x, or sorry, 2 sine of x. And then if we apply this phase shift, okay, then we're just going to move this whole thing over right by 2 units, or by pi over 4 units. Okay, so we just pick the whole thing up. And of course, I didn't draw it as a single thing. So why don't I just draw it with orange? We pick the whole thing up and we move it over by pi over 4 units. Now I know that this orange line here is at pi over 2. So if I move everything over to by pi over 4, then it looks more like this. Come on, gotta draw this right. Here we go. So here's my 2 sine of x minus pi over 4. Okay, so I'm going to erase my original graph of sine x now, since we've got the graph that we want. Okay, and now what is the graphical interpretation of this equation, which we've graphed below, being equal to 2? What is the graphical interpretation of this equality? Which x value is going to cause this to be true? Or how do we think about this equality in terms of the graph? Okay, let me ask a follow-up question. If I have f of x equals g of x, and I look at their graphs, and here's f of x, and here's g of x. which x values cause f of x equals to g of x. If I have the graph of two functions here, when are their equations equal to one another? I think you're right, Heidi. But let's go through this mental exercise to remind ourselves of how to use the graphs of functions to solve equations. If we have that the equations should be equal to one another, what should happen with the graphs? That's what I'm looking for, Justin. They should intersect. We have f of x is equal to g of x whenever the graphs of these two functions cross. So for these two x values, x1, and call this one x2, we have f of x1 equals g of x1, and f of x2 equals g of x2. So if we want to take the graphical approach here with our problem, and we've already graphed the equation y is equal to 2 sine of x minus pi over 4, then we should also graph the graph of the right-hand side, which is y is equal to 2. What does the graph of y equals 2 look like on the coordinate plane? What does y equals 2 look like? Very good, a horizontal line. Okay, we should have a horizontal line because y is describing the height, so the height is fixed and the x can just be anything it wants. So the graph of the right-hand side looks like this horizontal line with height 2. So here is y equals 2. And we want to know, ultimately, when are these two equations equal to one another? Well, as we've just recalled, two equations will be equal to one another when their graphs cross. So we want to find out, well, when does the graph of 2 times sine of x minus pi over 4 cross the line y is equal to 2? And it happens, we can see it on the graph, it happens at this point right here. So then all we're really interested in doing is understanding, well, what is this x value here? Once we find out what that x value is, then we will have solved for what is 2 times x minus pi over 4 is equal to 2. Okay? So how do we understand what this x value is? Well, this x value we can see is the point at which our function 2 times sine of x minus pi over 4 takes a maximum. To find out what that x value could be, we can think back to our original 2 times sine of x function, which looked like, this, basically. And we know that that one is going to take a maximum at pi over 2. So if we take the whole thing and up and move it pi over 4 units to the right, then the new x value here is going to be x is equal to, well, the previous maximum for sine occurred at pi over 2, and then we moved everything over to the right by pi over 4 units. So then this will be pi over 4 past pi over 2, which is then equal to 3 pi over 4. Okay, so this is the x value where this happens. Now we also have to remember that the sine function is going to continue repeating on and on and on forever like this, okay, in both directions. So we do need to consider a little bit about, well, what is the domain of interest? In our case, they say that x should be between 0 and 2 pi. So we found one value of x which is between 0 and 2 pi, and we want to say now whether there are any others. Well, I know that sine is 2 pi periodic, so I know that from 0 to 2 pi, it looks like this region, which is drawn in green in terms of my x values. My x values go from 0 up until, well, we'll go almost to the point where we've done a full revolution. So here's 2 pi. And then we'll have finished our revolution at 2 pi plus pi over 4. So I'm looking for x values which are in the green region, which cause a maximum to occur of our graphical interpretation of this trigonometric function. And I can see from looking at the graph that there's only one. Okay, there's no other maximums in this region. Okay, so to finish up, I would say basically, x equals 3 pi over 4 is my final answer based on this graphical approach. Okay, so that's one way to view this problem in a graphical way. I think the graphical way is a little bit loosey-goosey in some sense. But I think it's a perfectly valid way of thinking about this problem. Are there any questions about the graphical approach to this problem? Or any comments? Do you like the graphical approach, or is this totally unintuitive? Okay, maybe I'll comment briefly and say, I would imagine you might like the graphical approach a lot if you're very comfortable with graphing transformations of functions. If you're comfortable with graphing transformations of functions and you have a good idea of what the sine and cosine function look like, then you're going to be able to make great use of the graphical technique for most of these problems. If you're someone who really hates graphing transformations of functions, then I might try one of these other approaches. Okay. Maybe let's talk over the algebraic approach now. I'm actually going to run out of space. I better add a page, and we'll do the algebraic approach next. Okay, so remember we should have x, which is in 0, 2 pi, and our goal is to solve sine of x, 2 sine of x plus minus pi over 4 is equal to 2. Okay, so the algebraic approach is going to focus strictly on this equation here. Okay, so we want to focus on this equation, and I would say maybe the first step that we could take would be to try to manipulate this equation somehow. So let me ask you guys, is there anything I can do to this equation here to make it a little bit simpler than it is right now? Something algebraic. Very good, Abdul Rahman. We could divide both sides by 2, right? That would make this a little bit easier on the eyes. Divide by 2 and divide by 2. And then I'll be left with a new equation. It's equivalent to the old one. It just says sine of x minus pi over 4 should be equal to 1. Okay. So I know that sine of x minus pi over 4 should be equal to 1. Okay. Then I can take the following approach. I can ask myself, when is it true, or rather, for which inputs does the function sine take value 1? For which input theta does sine of theta equal 1? What do we think? Okay, we got a whole lot of answers in here. Sine of theta is going to take value 1 when the y value of the point on the unit circle is equal to 1. So it's going to take it at this point, 0, 1. And this is the point where the angle theta starts facing to the right and then is facing straight up. So theta is this angle here, which is a 90-degree angle, which is pi over 2. Okay, so we know that if theta is equal to pi over 2, then sine of theta is equal to 1. Any other values of theta? That cause sine of theta to be equal to 1, or just pi over 2? Let's consider what happens with 270. If we plug 270 in, we'd have an angle which looks like this, and it'd be pointing straight down, and then the point on the unit circle would be the point 0, -1. So that would cause our sine function to take value -1. So are there any other angles which point in this upward direction at the point 0, 1? I think Kamar's put it in. Sorry, I didn't see that one. Yeah, 5 pi over 2, right? We can take our angle theta and add 2 pi to it, basically. Okay, if we add an extra 2 pi, then theta plus 2 pi again points in this upwards direction. Or theta plus 4 pi, right? Would also be pointing in the same direction. So we have the following. Sine of theta is equal to 1 if theta equals pi over 2 plus 2 pi times n, where n is an integer. That is something like -3, -2, -1, 0, 1, 2, 3, ... One of these numbers. Okay. Now our goal is to find out when is x minus pi over 4 going to be an input, which causes the sine function to take value 1. And we know the form of every single input which causes the sine function to be equal to 1. Okay. So all we need to do now is say, well, we want sine of x minus pi over 4 to be equal to 1, which is equal to sine of theta. And we know this occurs if and only if theta is equal to pi over 2 plus 2 pi times n. And so if we have sine of some angle is equal to sine of some other angle, then we know that these two angles should be the same. So we can go ahead and equate also x minus pi over 4. And if we look at the relationship between x minus pi over 4 and the form which an angle should take to cause sine to take value 1, then we can find the following. We can just manipulate this algebraically. We add pi over 4 to both sides. And what do we get? We get x should be equal to 3 pi over 4 plus 2 pi times n. Okay. Now we need to finally satisfy the criterion. Remember, we required that x should be less than 2 pi and larger than or equal to 0. So we should consider, well, what numbers n could we plug into x such that this criterion would be satisfied? Well, we can try 0, then we get 3 pi over 4 is definitely between 0 and 2 pi. But if we plug in any other number like -1, then we're going to get 3 pi over 4 minus 2 pi would be less than 0. And if we plug any number which is like 1, we would get something which is larger than 2 pi. And any other number, we're just going to get something which is even further out of bounds than those. So this condition is telling us that n has to be 0. It is the only one. So therefore, x should be equal to 3 pi over 4. Okay, so this is a purely algebraic way of thinking about this. We didn't actually consider the graph of the sine function whatsoever. We used basically two facts. We used the fact that sine is a periodic function with period 2 pi, and we used the fact that sine takes value 1 when the input is some multiple of pi over 2. Or not multiple of pi over 2, some pi over 2 plus a multiple of 2 pi. Right? That's really including the periodicity in there. Okay, so when does the sine function take value 1? What input causes that to be true? And then we use the periodicity to find basically all values of theta such that sine of theta is equal to 1. And then we just said, well, if sine of x minus pi over 4 is going to be equal to 1, then the input pi over 4 should be an input theta, which causes this to be true. So we just equate the angles. Okay, so that's another way of thinking about this problem. Is there anybody out there who likes this approach much better than the graphical approach? Or anybody who says F that. There's no way I'm going to use this method on the exam. Justin says, I do. I do to what? You like it or not like it? Oh, Kumar likes both methods. That's good. Justin likes it. Yeah, I think it's good to have the versatility, the option of doing one or the other. You know, in this case, my personal opinion is that I think that the graphical approach is a little bit simpler. But again, it really just depends on what you're comfortable with. If you're comfortable with manipulating these equations algebraically, then by all means do so. If you're comfortable graphing transformations of functions, by all means do so. If you're comfortable with all three methods, I think probably the easiest one is the graphical. So that's kind of an advantage. If you can be comfortable with everything, then you get to kind of have your pick of the litter and choose the easiest method. But yeah. Okay, let's see the final interpretation. We have sine, 2 sine of x minus pi over 4 is equal to 2, which again, I'm going to simplify this to say sine of x minus pi over 4 is equal to 1. Okay, so I'm going to do a little bit of algebra up front to simplify the unit circle interpretation. And we also have that x should be less than 2 pi and larger than or equal to 0, right? Okay. So if I want to use the unit circle to understand what's happening here, I need to remember what sine means in terms of the unit circle. So let me ask you guys, what does sine mean in terms of the unit circle? What is the sine function? What's the relationship between the sine function and the unit circle? Okay, a bunch of y's coming into the chat. That's right. So we can, the sine of theta is the y value of the point on the unit circle corresponding to theta. Okay, so we have an angle here, and the sine of this angle outputs the value 1. So in terms of the unit circle, what we're going to do is the following. We are going to search for an angle theta which is between 0 and 2 pi, which remember are both facing in this direction. Okay, so we're going to start looking at angles which are basically anywhere in the first iteration of the unit circle, or the first rotation of the unit circle. And what do we want? We want our angle to have the following property. Our angle theta should have, or our angle x, or we're interested in what should x be, right? So if our angle here is x, and then we count back from it by a pi over 4, And we get this new angle here, which will be this angle is x minus pi over 4. We want the angle x minus pi over 4 to point at the point on the unit circle whose y value is 1, which is the point here, which is 0, 1. Okay, so if we trace back our angle, we count it a little bit backwards by pi over 4, okay, which is 45 degrees, then that angle, that adjusted angle, should point directly up. And we have that the angle which is in red is x itself, and so x itself should be between 0 and 2 pi. So if we look at this, it's not too hard to see that, well, x minus pi over 4 should be equal to pi over 2. And then we're going to find that x itself then should be equal to pi over 2 plus pi over 4, or 3 pi over 4. Okay, so that's the final interpretation of this problem. We can look at it through the lens of the unit circle as well. Okay, so we just think of an angle x such that if we basically count backwards by 45 degrees from that point, then sine is going to be pointing at the point on the unit circle with y value 1, and there's only one point on the unit circle with y value 1, and there's only one x value between 0 and pi over 2, or 0 and 2 pi, such that if we count back by pi over 4 from it, we're going to be pointing at that pi over 2 spot. So that's the final interpretation. That's kind of a nice one, actually. Okay, so what is this all to say? This is all to say that, as usual with trigonometry, you've got a lot of options for how you can solve this problem. So here's 3 different ways that you can solve it. You can use the graph of the trigonometric function. You can manipulate the algebraic equation and use the periodicity. Or you can take a look at the unit circle and try to interpret, what does the sine of an angle mean in terms of the unit circle? And what can I say about the angle if I know what the y value is? Okay. All right. Any comments or questions on this problem about these 3 different approaches that we took? Okay, seems like not. My comments for you guys would be, I guess the best advice that I could give would be to be aware of all 3 of these methods. Okay, and practice some problems and maybe practice trying these different methods and see which one you find to be the most convincing or just the easiest for you to understand. There's no problem with taking the path of least resistance in mathematics. If you find that one of these is far easier than the other, then you should use that method. there is, I think, some benefit in understanding the connection between all three of these methods, because then you will kind of really have a mastery of this material. If you can check all three of these, then you can also use each of them to kind of check your answer on the other method. If you get one thing for the graphical method and then you use the algebraic method and you get the same thing, that should give you some confidence that you've done the problem correctly the first time. You can also do that. Okay, Kumar says he thinks the first two were more understandable than the last one. Yeah, I think there are a lot of students who, myself included, when I first started doing trigonometry, the unit circle was not my favorite thing. But I've since grown to kind of really like it. In any case, I think it's a powerful tool to understand. Okay, we got about 12 minutes left. Oh, this is a great problem. Okay, so let's entertain the idea of another problem. Okay, and the problem says we're supposed to find all solutions of this trigonometric equation, which looks kind of crazy at the start. We have 2 times sine squared of theta minus 5 times sine of theta plus 2 is equal to 0. Okay, so one thing about this problem that's really kind of intimidating is this sine squared theta here. The sine squared theta term is really, I think, the most intimidating part of this equation, because if we just got rid of it, then the rest of it would just be figuring out how to find the angle theta such that sine of theta is equal to negative 2/5, right? And that wouldn't be so bad. But here we've got this equation. So let me ask you guys, is this equation reminding you of any sorts of equations which we used to solve before we started working on trigonometry? That's my hint. You take a minute or so to think about that. I'll let that question kind of hang for a minute. Yeah, it does kind of look quadratic, doesn't it? Very good. And of course, Abdurrahman, yeah, or Kumar, a quadratic is a polynomial, so that's also a good answer. Okay, it's a polynomial. It looks kind of like 2x squared minus 5x plus 2 is equal to 0, where x is equal to sine theta. So, if I want to know how to solve this equation, I can use the fact that I already know how to solve this quadratic equation using x. So let's solve the quadratic equation using x. Well, if I solve it using the quadratic equation, what do we get? Well, we get negative b, that's 5, plus or minus the square root of b squared, that's 25, minus 4 times 2 times 2, that's 16. And this should all be divided by 2a, which is 4. So I can simplify this. This would be 5 plus or minus the square root of 9 all over 4. So x is going to be equal to either 2, or if we do the minus, then we get 5 minus 3 over 4 would be 2 over 4, which is 1/2. So returning to our substitution, that x should be equal to sine theta, we know that we should have sine of theta should be equal to 2, or sine of theta should be equal to 1/2. Let's focus on the first one. Sine of theta is equal to 2. Can someone tell me which values of theta cause this to be true? What values of theta can we plug into sine of theta and get 2 as our answer? Yeah, very good, Abdul Rahman. It's actually undefined. Why? Because sine of theta is expressing the y value of a point on the unit circle. If the y value of a point on the unit circle is 2, well, it's not a point on the unit circle, is it? Because the unit circle is here, and the line y equals 2 is all the way up here. And there's no intersection. So there's no values of theta which cause sine of theta to be equal to 2. Or if you look at the graph of sine theta, what values does it take? Its y values between 1 and -1. Right? So asking which values of theta cause sine of theta to be equal to 2 is nonsensical. It makes no sense. So we're just going to kind of ignore this solution to our quadratic. Now let's focus on this other one here. Sine of theta is equal to 1/2. Well, if sine of theta is equal to 1/2, we can draw the unit circle. We should have that the y value of theta, or of the point, which theta points at, should be 1/2. So we draw in the line y equals 1/2. And then we can see that there's 2 points on the unit circle that are going to satisfy this equation. There's the angle theta, which points here at the point question mark, comma 1/2. And then there's the point, the angle theta, which points at this point over here, which is the point question mark, comma 1/2. Its angle looks like this. Okay, so if we solve for the first one first, well, we know we have a triangle, right? And if we brought this triangle out, what would it look like? Well, it would look like this, kind of. And we know that this length here is 1/2 because the height of the point is 1/2. And I claim that we know the length of one other side of this triangle. Can someone tell me what it is? What is the length of one other side of this triangle here? Yeah, 1, right? Because the radius of the unit circle is 1. I know that this length on the, well, that doesn't show up very well. This length, which is highlighted on the unit circle, should be 1 because it's the unit circle. So I know that that's the other side length. And so if these are the side lengths, what should this other side length be, this final one? Do we know it? Is this a special right triangle? √3/2, very good. And we're interested in knowing what is the angle theta. What is the angle theta? It faces the shortest side on a 30, 60, 90 triangle. Where's my phone? Oh. Yeah, exactly. Theta should be 30 degrees, or pi/6. Okay, in the other case, we've got another triangle. It's another 30, 60, 90 triangle, only this time we know that this angle, which is inside here, is 30 degrees, which means that theta, the green one, should be 180 minus 30, which would be 150, or 5 pi/6. So the solutions to the equation, our original equation, which was 2 sine squared theta minus 5 sine theta plus 2 is equal to 0, are the values theta equals 5 pi/6, or theta equals pi/6. Final question for the class. Are there any other values of theta other than these two? I've got 5 pi/6 on the board already. These two both work. That's right, Om Kumar. Om Kumar's got the right idea. We can add 2 pi times any integer to both of these. And guess what? The value of the sine function will be the same due to the 2 pi periodicity of the sine function. And we were asked to find all solutions of this equation with no conditions on theta. So since we have no conditions on theta, we should really express all possible solutions. And we would say n is an integer. Okay. Well, thanks everybody for your help today. I hope you guys found this enlightening. I really like this quadratic inform problem. It's really a great problem. Hopefully you guys found this helpful and kind of a little bit more engaging than my usual kind of lecture mode, which I've been in lately. Trying to get you guys involved a little bit more. So that's it for today. This concludes the material that will be covered on the exam on Thursday. I'll see you guys all tomorrow for the review. Please bring questions. Otherwise, I'll have some stuff for us to work on. And then I'll also have office hours after class tomorrow. So that's it for today. Thanks, everybody. Yep, my pleasure.